Okay, so today on the bench we have a little eBay special. I bought two of these, this one here and that one right there that's actually attached and working right now. These are wideband 2-watt amplifiers, so they eBay listing, these were a little bit over $15. I think it was like $15 and some change plus shipping from China, straight off the boat from China. They cover from one to advertised. I'll move the camera over a little bit. I copied this down straight off the listing. From 1 to 930 megahertz. Maximum input power is 1 milliwatt or 0 dBm. Output, advertised output is 2 watts at 10 megahertz, 33 dBm, and then all the way up to 1 gigahertz. Now it says 930 megahertz, but they did have a power output listed at 1 gigahertz, but that at 0.8 watts for 29 dBm. So that's actually a fairly flat output response if you consider we're going from 10 megahertz all the way up to 1 gigahertz on a fairly simple circuit. There's only 3 transistors on there. There's not a lot to this thing. So operating voltage is 12 volts DC, current draw from 300 to 400 milliamps, and that depends on how much it's amplifying. So it depends on the input level. Now this is kind of similar to, I did a video some time ago. I got some little tiny amplifier boards. I wanted to show that if you have a frequency counter or a piece of test equipment that has doesn't have the greatest input sensitivity, and working on radios, occasionally you'll run into that. You hook up a frequency counter to a circuit and there's just not enough there. Your frequency counter just can't lock on it because the signal's not big enough. And those little tiny ones are fine for doing stuff like that because they're very small. They don't, honestly, the output level is still very low on it. It's fine for measuring with an instrument, but the nice thing about those is the output really isn't high enough to damage test equipment. If you hook this up to something like the input of a frequency counter, it depends on your equipment. This thing may nuke the front end of, or spectrum analyzers or whatever you might be hooking up to. You would not probably want to use this unless you really know what you're doing. You might even need to put some attenuators then on the input or the output, one or the other. Now, they did not have in the listing for this one that this was variable, but I kind of assume the layout, the principle here is going to be the same as that little tiny one I did. And in that listing, that amplifier was listed as variable output by just adjusting your voltage down. So I've actually tried that with this. Yeah, if I turn the voltage down on it, the gain goes down. So, if you do want to use this variable, kind of like the power supply I'm running this off of is a laboratory style power supply. So yeah, if I wanted to turn the gain down, all I'd have to do is just turn the voltage down basically. But I wanted to do some testing just to see, are these specs anywhere, fairly close, and what kind of gain or real world do we get out of this? Is it a piece of junk or does it work? So, like I say, this one is hooked up and running. It's actually been on for about an hour. I'm shoving minus 10 dBm into it, and barely warm. 96, 97 degrees. Heat sink's around 98. Now, when I did notice when I get up to 1 gigahertz, I get a temperature up to maybe 110 degrees, and that's sitting flat on the bench. There's no fan. It's just been sitting here, just humming along for about an hour or so. Now, I wouldn't call it modifications, but I did do some improvements. For starters, not an improvement. I had to hook a power cord up because it just has 2 solder pads here for your power cord. So I soldered permanently, attached a power cord here. Then on the other end of this, I just have a double banana jack because I'm just going to leave this one just in case I ever need it. It'll have the power cord permanently attached to it. When I first got them, I have not done it to this one. I have done both of the next 2 things to this one. I removed the 4 screws to check, and no, there is no heat transfer compound in between this board and the heatsink. Now granted, it doesn't get that hot. Do you really need to add heatsink compound? Probably not, in all honesty. Is it going to hurt anything? Definitely not. So I did that. You can actually see some white stuff through some of the throughs there, the vias. So they do have vias. It's a lot clearer to see here because there's no heatsink compound, but there are vias around the transistors to help conduct some of that heat down to the bottom layer. The top layer is silk screen. When you pull this board off, The bottom is solid copper. It is tinned, but it is not silk screened. So, like I say, I added some heatsink transfer compound to it. The other thing that I did, there's not a lot of solder on these. Honestly, they're probably just, again, they're just fine the way they are. They're soldered down solidly. They're not going anywhere. I'm a paranoid type person, so I added some flux, and you can see there's nice amount of solder on the tabs on all of those now, so I have really good thermal connection to this board, because I hadn't turned it on yet to even check to see how hot they got. After I turned it on and felt how non-hot it gets, I really didn't need to do that probably, but it's not going to hurt anything. Better thermal conduction's always better than not enough. So what I'm running, actually we'll just disconnect the amplifier, and so you can see there's no hocus pocus. So everything I'm using here is Pomona connectors. The cables are Pomona. Somewhere on these cables, actually. I dropped the camera. Yeah, here they're Pomona cables. All of the adapters. If we can get it to focus on that. It's not. Yeah, you can see they're the BNC to SMA connectors. They're all Pomona adapters as well. And somewhere I have a barrel connector laying around here. Just want to show no hocus pocus or funny stuff here. So there's that connected together. The test setup I have, if you follow both of those cables. So here they are up to the communications test set here. So I have the signal being output from this jack, and then comes back in to the input on this jack. What we'll be looking at is the screen here. Got my camera mounted full swing here. Are you going to focus on that line or not? If I turn this overhead light off, will it like it better? The only problem, this screen is just so bright, it's hard to get this camera. It just blinds it. Come on, yeah, that's pretty good. You can read the text. Basically, all you need to see is the peak, the frequency, and the output, at the peak of the marker. So, I'll be writing down this stuff. So right now, what I'm shoving into that little amplifier is at a frequency of 20 megahertz. I'm shoving minus 10 dBm into it, and we have a peak, an output of minus 10.2. And that's not right. That's because the that's not the amplifier in circuit. That was the generator, because I remember I wanted to show you the connection over there. So now let's hook the amplifier into circuit. That looks better. Okay, now we actually have some gain. So at minus 10 dBm input, we have a output power level of plus 32.3. dBm. Now what I'm going to do is change the output level to minus 50. And our peak is now at plus 1.5. And now minus 100. Now, I picked minus 10 dBm. It says the maximum input is 1 milliwatt or 0 dBm. I never like to run anything at its maximum. I always feel better running it at a little bit reduced input power. Equipment tends to last longer, everything. So, like I say, I purposefully picked 10 dB lower than the maximum input on the amplifier. So, what did I say? So we're at 100 minus 100 dBm input, and we have minus 48.5. Now let's change frequency to, what did I say, 500 megahertz. And analyzer center, 500. Marker, peak. So we're still at minus 100 dBm, but now at 500 megahertz, and we have an output of minus 61. So there is a difference there. The gain definitely goes down as you go up in frequency. Minus 61.7. And now we'll change the level to minus 50. No, not 560. I'm trying to work around the camera here and erroneously hitting buttons. So at minus 50 dBm input, we have an output of minus 11.6. And I'll go over the settings for the spectrum analyzer when I get done here. And what, now minus 10. And we have an output of plus 27.7. And now we'll change the frequency to 1 gigahertz. Analyzer center. And at, again, that's the input levels at minus 110. Or minus 10. We have an output of positive 19.9. And minus 50. Minus 19.7. And minus 100. We have minus, it's bouncing around there a little bit, and I think that's probably it. It's not quite as stable up at the really high frequency, but still right at minus 70 dBm. So now the actual setting, let's go back to, let's say, 500 megahertz. Analyzer. So, I have the span on the analyzer set to 100 hertz or 0.0001 megahertz. I have the resolution bandwidth set to 20 hertz. I wanted to do a fairly narrow span and a fairly narrow resolution bandwidth. The narrower your span and the narrower the resolution bandwidth, the better accuracy you have. Now, I could have gone down. This will actually go down to 10 hertz. But you can see how slow it traces. It can take a long time. And I can set the span down, but it starts to really become an arc if you get this, your span down. I mean, we could go down to like 0.0000, whatever, 1, 2, 3, another 0. Oh no, not that far. 0.00001. Yeah, I mean, if you really want to get narrow, but so actually something I didn't look at. Let's see what kind of, because anytime you amplify something, you're going to have, harmonics being generated. So the center frequency is at 500 megahertz. So let's set the span to, I don't know, let's say, actually let's go down to a smaller frequency, something like the 20 megahertz. That way the multiples won't be so gigantic. And we'll just set the span to 100 megahertz. And resolution bandwidth, 10 kilohertz. We can drop down just put that back to, let's do 10 kilohertz. Generator frequency 20 megahertz. Levels at, let's increase the level here to minus 10. No, not minus 120, minus 10. So, yeah, we can see we definitely have a bunch of harmonics, and there's going to be other, mixing products in here. But it's to be expected. It's an amplifier. It has no filtering on the output because they don't know what frequency you're going to be putting into it. So, harmonics are to be expected. Let's actually set the stop frequency. It's at 110 right now. Let's just go out to, let's say, 500 megahertz. Oh yeah, just look at that. Very harmonic rich. But again, to be expected on a wideband amplifier. They can't really filter out any of this because it's meant to be wideband. It's meant to be able to take any frequency at the input and amplify it. So, you know, they can't go sticking output, you know, filter circuits on there. And even if we go out to the maximum, this thing will do 2.7 gigahertz. So, yeah, you can see it drops down to around here. So if we go to 1 gigahertz, 500 megahertz. Yeah, so it's by the time you get out to 500 megahertz, it's so small. You're down, what, 60 dB by the time you're down there. But yeah, as long as you realize, and that's going to be common to any type of wideband amplifier, harmonics. Just get my laboratory amplifier down there. Now, it's nowhere as bad as that, but it does have harmonics. It's just part of amplifying things is having harmonics like that. So that's just something to remember when you're doing something like this. If you're using little guys like this, expect to have a lot of peaks coming out of that thing at even and odd order mixing, you know, frequencies. You're definitely going to have high peaks at your second, third, fourth, fifth. You know, good Lord, this thing probably goes out 20th. If I put the resolution bandwidth out, well, actually, let's just take an example. The heck am I putting in this? 20 megahertz. So, you know, second harmonic would be 40 megahertz. So let's just see at center 40, span. Go down to all the way down to 10 hertz resolution bandwidth. And you can see we've got a minus 12.9 dBm signal at the second harmonic. And if we go out to analyze our center frequency, let's say 60 megahertz. Yep, and go out to 80 mega. Oh, not 980. Trying to work around a camera here is a pain in the butt. 80 megahertz. Yep, another peak. Go out to 100. So, you know, every 20 megahertz, you know, harmonics, there's going to be a peak. And the same thing if I was to set the generator at, let's say, the generator frequency at 100 megahertz. So, you know, center frequency, so that's the signal actually coming out of the amplifier. And then if we go out to the second harmonic, that would be 200 megahertz. So we'll set the center frequency to 200 megahertz. And there's our harmonic. And if you go out to 300, there's your third harmonic. Fourth harmonic. Fifth. Actually, let's just go out to, let's say, a gigahertz. Yep, there's the 10th harmonic. It's getting down there. I don't know. Let's try the 15th harmonic. 1500 megahertz. Yep, still measurable. Let's try the 20th harmonic. Is it getting down in the mud yet? Nope, still measurable. It's still there. The 20th harmonic. Well, as wide as this thing goes is the maximum's 2.7 gigahertz, so let's try that. So that would be the 27th, oh yeah, 26.99, yeah. So let's try 26. Yeah, it won't actually go to 27, it'll go to 26.999999. So let's actually try 26, or 2.6 gigahertz. Nothing measurable there. 2400, no. 2000, that's the 20th. Oh, teeny tiny little peak. So it's measurable out to the 20, just barely, but out to the 21st harmonic. And actually I could change the scale. I'm sure we can measure down even lower. But yeah, so it's just something to be aware of. Really, really, to set the span to... Let's put that to auto. But, so, you know, as long as you know that ahead of time, anytime you use a wideband amplifier like this, you're going to have lots of harmonics. Let me get some light back on here. So, but there you go. There's the results. You know, to frequencies, I picked 20, 500, and 1 gigahertz. So you can see it, you know, 1 gigahertz minus 110 dBm input, we had 70 dBm output. So, you know, basically exactly 30 dBm amplification. And at minus 10 dBm, we had almost 20, so I'd call that right around 30 dBm. So, you know, at 1 gigahertz, it's doing 30 dBm of gain, and they called for 29. So, actually, it's doing a little bit better than expected. At 500 megahertz, minus 100 in, minus 61.7 out, to, you know, minus 10 in, to positive 27.7 out, and down at 20 megahertz, of course, getting a lot more gain. You can see that we're getting a lot more gain the lower you go in frequency. So yeah, that's I think that's pretty good. So for the money, like I say, it was $15 and some odd cents plus shipping. I think that's a fair price for one of these things. I can see all kinds of applications for this. Shoot, you could use this for a little QRP transmitter, a little 2-watt transmitter. Now I want to get. Like I say, I've shown the little tiny ones before. They're good for probe amplifiers, like probe preamps. These you could actually use for transmitters, for little, like I say, QRP rigs. They do make these things a lot bigger. I know they have, I think, 5 and 10 watt, but if I'm not mistaken, I think I've seen 50 watt ones. I might get one of those. They get rather expensive, and you're starting to get kind of big on the heat sinks. It's kind of like that laboratory amplifier one over there. That one's got a massive heat sink in it, but it's to be expected. Really broadband amplifier. It's very, very inefficient because it needs to cover such a wide range. So they do tend to generate a lot of heat for that reason. But yeah, I'll see what the next 1 or 2 sizes up are. I may get some of the other ones just to try them out. Now, what can you use like something like this for? Like I say, you could use it to as an amplifier for a very small little transmitter, a little home-built transmitter. Now, 2 watts isn't really enough to drive an amplifier. It depends on what type of amplifier you'd be driving. You know, another amplifier. I'd like to get like a 5 or maybe a 10 watt one and see for like low drive style amplifiers if it would be suitable. Because actually the reason I got that amplifier was for testing amplifiers. Problem being, most signal generators don't have enough output, you know, because this is the output from the signal generator up there, don't have enough output to directly drive an amplifier. And I don't like using a radio to drive an amplifier. I like to use a very spectrally pure as I can get signal coming out of a good signal generator. That way I can take good quantitative measurements. I'm not using a radio that might have all kinds of crap coming out of it. I can use a good clean signal coming out of an amplifier, or out of a signal generator, but I can run it through my, I got that laboratory amplifier just for that reason, to be able to boost that signal, and then I can use that laboratory amplifier to drive the amplifier I'm actually testing, and then I can attach a sample port to it and measure. You know, I can measure the input and the output to monitor the input and output, you know, harmonics and any distortion products there might be. Like I say, this really wouldn't be big enough to drive some of those amplifiers, but you know, if I can get these, and I'm pretty sure they, like I say, they make 5 or like 10 watt ones. Those would be fine for that. But I think they make like 50, maybe even 100 watt. I really need to check. I'm just, yeah, my backside cheeks are just kind of flapping at the moment there. It's been a while since I looked, but I do know the Chinese do make some bigger ones. I'm going to get them though. So expect to in the future. I did a review on that little tiny one. Bought 2 of these, did a review on these, so I'll see what other bigger ones are out there, and we'll give them a try as well. You know, it never hurts to have amplifiers around, because you never know when you need to amplify a signal out of a piece of test equipment, or you're trying to take a test measurement. The little small ones, like I say, they're great for preamps on probes. So yeah, I'll get some of those other ones. So, you know, at some point in the distant future, you may be seeing even more little review videos on these little cheap, fresh off the boat Chinese amplifiers. Hey man, they work for the price. You can't beat that. I mean, shit. You walk into a store here in the United States, they probably charge you close to that just for the aluminum heatsink on this blasted thing. They can make the whole thing, send it across the planet to the other side of the planet for less than I can probably buy that heatsink in this country. I'll never understand how they can do that. Cheap labor, what else? Yeah. But, so, there you go. Cheap Chinese amplifier. I gotta give it a thumbs up. I'd say the little critter works pretty good. Harmonics, to be expected, wideband amplifier. Doesn't get hot. Like I say, around 100 degrees is the maximum temperature I saw on that thing. 100, 110 degrees. It just idle. They definitely have enough heatsink there. Like I said, the only things I did, I really didn't need. I'm going to suggest you don't have to do that, and I'm not going to do that to this one. Solder, increase the amount of solder on the transistors. But I would recommend putting some heatsink compound in between there. That definitely is not going to hurt. And that may be one reason this, up on the top side here is running cooler, because it has very good thermal conduction to the heatsink. There's actually heat transfer compound in there, where before there was none. So that might be the one thing I would recommend. Add some heat transfer compound. But there you go. There's my really quick testing of a little amplifier and the gain results that I got.